In the next couple of sections, we're going to look at thermodynamics and kinetics, some topics from general chemistry, and see how they relate to organic chemistry. One of the main differences is that we won't actually be calculating things. We'll talk more in terms of how we understand thermodynamics and kinetics and how they can help us understand what's happening in a reaction. Thermodynamics describes energy in equilibrium, while kinetics, when we look at that, refers to rates of reactions. So if we're going to talk about energy in equilibrium, one of the most important things for us to talk about are equilibrium constants. So KEQ is the equilibrium constant. And to get KEQ, we have to take a reaction. So if we have A plus B goes to C plus D, then we can define KEQ as the concentration of the products over the concentration of the reactants when it reaches equilibrium. So how much of their products are there versus how many reactants are there at equilibrium? So if KEQ is greater than 1, what does that mean? The numerator is greater than the denominator, which means that there's more products than reactants. And we'd say that products are favored by that reaction. Or as it's drawn here, the equilibrium lies to the right. Now if KEQ is less than 1, what does that mean? If KEQ is less than 1, that means that this number is greater, the denominator is greater than the numerator, so there's more reactants than there are products at equilibrium. So more reactants than products at equilibrium. Which means that reactants are favored in this reaction. Or the equilibrium lies to the left. So I could draw something that favors the right. I could draw my equilibrium arrow more like this, where that's like a KEQ greater than 1. The equilibrium lies a lot to the right with just a little bit to the left. I could also draw the opposite one, the second one, where the equilibrium lies mostly to the left and just a little bit to the right. So we can draw these with uneven arrows. If KEQ is really large in one direction or another, then that's when we draw just a single arrow. So any reaction can be reversible, but if it lies like 1,000,000 times or more to one side than the other, we can say, well, effectively this only goes one direction. If it goes that direction 1,000,000 times for every one, it goes the opposite direction. And in fact, some of our KEQs are even much greater than that. So at that point, then we'll draw just a single arrow and not draw the reverse arrow, because effectively we don't get any of the other material. So if you want to look at a real chemical example of that, you can take something simple like sodium hydroxide reacts with HCl to form water plus salt. All right, so you pause the video for a second and draw out the KEQ for this reaction. So KEQ equals the concentration of water times the concentration of sodium chloride divided by concentration of sodium hydroxide times the concentration of HCl. Okay, and of course all of these concentrations are all at equilibrium. And one of the keys to this is that for a reaction to be useful, it needs to favor the products. Otherwise, we can't really get that reaction to go. So there's some ways that we can do it to force it to favor the products, and we'll talk about those occasionally during class as well. And in effect, what equilibrium always favors is equilibrium always favors the lowest energy species, or the lowest energy side of the reaction. So that gets back to my question that I asked from the very beginning. If I say why, the answer is lower energy. Why does equilibrium go a certain direction? Lower energy. So we have to find ways to make it lower energy if we want a reaction to occur. So now we can revisit our reaction coordinate diagrams. And I can look at a reaction like this one. And remember, we said that this is going to be exothermic, right? Because the energy at the beginning is higher and the energy at the end is lower, so it gives off energy, right? This releases energy. So delta H is negative. But we can also look at the same reaction coordinate diagram and say something about KEQ. So if the reaction is favored, the products are favored, right? Here's our reactants. Here's our products. If our products are favored versus our reactants, then we can say that KEQ is going to be greater than 1. So now we're starting to relate equilibrium constants with energy. And they do relate to energy, although they don't relate directly to delta H as easily. We usually relate them to delta G. So delta G is Gibbs free energy, delta H minus T delta S. So it's related to temperature. Right, so delta G is going to be temperature dependent. So delta G of formation, delta G0 is delta H0 minus T delta S0. We can write that same reaction. So it's related to the enthalpy, although it also has this entropy term. Remember, delta S is entropy. Delta H is enthalpy. And delta G is Gibbs free energy. And again, we've seen back here that the energy and the equilibrium constant are related. So the equation for that is delta G equals minus RT natural log of K, KQ, where R is gas constant, 8.315 joules per mole Kelvin. T is the temperature in Kelvin. And there's a log relationship between the two, a natural log relationship. We can also write the equation for K. So KEQ then equals E to the minus delta G over RT. So given either the equilibrium constant or the Gibbs free energy for a reaction, we can calculate the other one. So now let's look at the opposite example. Here's my energy. Here's my reaction progress. Here's my starting material or reactants. Here are my products. So now this reaction, energy had to go in to make this reaction occur. Makes it endothermic. Right? Energy went in, so it requires energy. The other one releases energy. This one requires energy input. To make the reaction occur. Delta H is positive because of the energy input, and KEQ will be less than 1 because reactants are favored. The reactants are lower energy.